All right. Well, why don't you get out your notes thingy there. So, yeah, this is chapter 20. We sort of do that right now because that gives us a little more insight into the structures of molecules that we'll be working on sort of in the next chapters coming up. But after we do 20, we go back to 11 and then go in order 11 through 19 in the textbook. So it's very interesting they decided to remove 20 from this version of the textbook. Part of it is because this is principles of the principles version of the textbook has a little less information, sort of the essential information. So it could be they figured that not enough people do the organic chapter, but every school I know of uses it. So, well, whatever. Alrighty. So, organic chemistry is what chapter 20 is all about. And you may have heard this word organic in several different circumstances before, like in the grocery store, organic has to do with how things are farmed and pesticide-free and stuff like that. But it's a very simple definition in chemistry. What organic chemistry is, it's just the study of carbon-containing compounds. Okay? So just very simple definition, and we're going to have one chapter that'll introduce us to the chemistry of carbon-containing compounds. But those of you that are going on to many science majors, any kind of biology type majors, things, any kind of medicine or pharmacy or anything like that, you're probably going to have to be taking more chemistry. And so first year is sort of Gen Chem 1 and 2. Second year is organic chemistry 1 and 2. So there's an entire year worth of study in organic chemistry, and I actually have my master's degree in organic chemistry. So it's a huge field of study involving carbon-containing compounds, and we're just gonna deal with just one little bit of it. So yes.
Okay. So in bio, you said something about carbon dioxide not being counted as an organic compound.
So yeah, why is that? So we're pretty much a lot of it has to do with right here, compounds containing carbon-carbon bonds. And that's not even the best definition because CH4 is considered organic, but CO2 is considered inorganic. So I don't know. I don't have a great answer for that. CH bonds are more similar to CC bonds than CO bonds are. So CO bonds are kind of the exception. They're organic compounds on the whole are mostly CC bonds and a lot of CH bonds and a couple of CO bonds. So I guess we can understand how CO2 that only has CO bonds would be much different in its properties. So yeah, CO2 behaves more like inorganic compounds. Organic compounds kind of have their own set of properties and so on. So, but a lot of it is just kind of a historic designation too. So the carbonate anion is definitely inorganic because we can make ionic compounds like sodium carbonate and calcium carbonate and things like that, and those behave like any other ionic compound would. Right? So let's remind ourselves of the way that carbon bonds. Carbon has 4 valence electrons, right? So if it was to have 0 formal charge, how many covalent bonds would carbon make? What do you think? 4? Right? If you imagine, right, carbon like that, if you think of something like CH4, each covalent bond gives it access to another valence electron from the atom that it's bonding with. Okay? So carbon is going to make 4 covalent bonds, and the ways that can happen, right, these shapes end up being, if we have all 4 covalent bonds, that's tetrahedral. And the proper way to draw a tetrahedral shape is like this, where you have 2 of those in the plane of the paper, and then the wedge one is coming out towards you. Let's close the door. And that dashed bond is going back into the paper away from you. So, well, sometimes, if we're not entirely concerned with shape, we'll draw it like that, but that's not technically the correct shape. So it's not automatically wrong if we draw up, down, left, right, but that's not a realistic depiction of how those bonds actually form. Okay? So, anybody remember that bond angle?
108.
Close. Yeah. There you go. Ideally 109.5. Okay. You're only 1.5 degrees off. That's not bad. So that is the ideal tetrahedral bond angle, and anytime carbon has making 4 covalent bonds, that's pretty much what we're going to have. Lone pairs will distort that bond angle, but a carbon with no formal charge cannot have any lone pairs on it. So it's pretty much going to have that ideal bond angle almost all the time. It's possible to have a trigonal planar carbon. That's a carbon with 3 electron groups to it. What would the bonds look like for a carbon that has just 3 electron groups that are repelling each other? What do you guys think? Remember, we still need 4 covalent bonds total. Yeah, if we had 4 single bonds like that. If now we have a double bond, okay, and 2 single bonds, that's our 3 electron groups. Okay. and 120. That's just sort of triangle kind of shape. Okay. So 4 electron groups, 1, 2, 3 electron groups, essentially 3 sigma bonds, and then an additional pi bond on that one to make the double bond. Remember, sigma and pi. Okay. So then there are 2 ways to do linear. Linear is just 2 electron groups. So what's one way of combining those 4 covalent bonds together into just 2 electron groups? What do you think? Let's do symmetrical 2 double bonds. Okay. And then what's the other way? Yep. 180 in both cases. Okay. So that's what we're going to focus on now, sort of in this chapter. And because it can make 4 bonds, okay, and because the carbon-carbon bond is very strong, there's essentially endless possibilities for making large molecules. It can make big long chains, it can make rings, big branches, okay, all kinds. So, and because that carbon-carbon bond is very strong, almost no other element has very strong bonds to another atom of its same type. Okay? So the carbon-carbon bond is stronger than the HH bond or the OO bond or the NN bond, for instance. Okay? So it's pretty much the only element that you can make big, long chains out of. Okay? So we're going to categorize a little bit just to be able to understand these things. Alkanes, alkenes, and alkynes have to do with types of bonds. So for all of them, it's going to be mostly single bonds, but the addition of a double bond makes an alkene, a triple bond makes an alkyne. Okay? And then there's an entirely different class, aromatic, that includes benzene rings, and we'll talk exactly about what those are. But let's start with